Is the lecture for additive manufacturing, lecture number 9. And we finished the discussing the powder-based fusion processes that are similar to the selective laser sintering and metal-based additive manufacturing. So now we are going to be going into extrusion-based processes, which are typically similar to the ones developed by companies like Stratasys. So we talked about metal-based additive manufacturing techniques, and we will talk about polymers and composites in this lecture. I'm not going to go in great detail, but I would appreciate if you would go online and look at notes and things like that for these processes. So, what is the current status of additive manufacturing for polymers and composites? Many of these processes started in the early to mid 90s. In fact, there was a number of techniques that were developed by Scott Crump and Bill Priedemann and others at Stratasys. But uh, ever since the Stratasys patents expired in approximately 2009, if I'm not mistaken, because I think the original patents issued in 1992. So after 17 years, they expired around 2007, 2008, 2009. So after that, there was an explosion of techniques that were developed, techniques and machines that were developed by many different people. So some of the implications of this was that the original Stratasys printers used to cost $100,000 plus. The computer that had to control that machine was was wax deck based, so they used to cost about $100,000 plus. So you could think that even the simplest of the machines used to cost about 250,000 to about half a million, depending upon the envelope size. Very quickly, Scott Crump is probably one of the smartest businessmen I have ever known. He and his daughter, they started bringing down the price of these machines quite drastically. After 2009, there were many different companies that started making similar machines. In fact, if you go to Staples, you can now get one of these machines that used to cost $100,000 plus. You can get them for $300. So, what a company called MakerBot, I don't know if any of you have seen that. Uh, I believe that there are MakerBots, many MakerBots on the OSU Stillwater campus. They were, when they originally came on the market, you could buy a complete set of parts that you could assemble, and it would cost you about $400. But then MakerBot may change their business model and said that they would sell the machines that was put together for you for approximately $1,000. Then Stratasys went and took them over, and now those prices of those machines are approximately $2,000 to $3,000. But the interesting thing is that MakerBots, the market for MakerBots has actually gone down after Stratasys took them over. And in fact, they have been losing money. And I think that the reason is that the prices are still unaffordable for an enthusiast or a high school student, if you have to do that, I think the only way to do it is by having these machines under $99. It needs to be like an inkjet printer that costs $99 plus. And now that inkjet printers are $49 and $39, I think the prices of these machines has to come down. And that is the only way to make additive manufacturing popular and accepted by the general public. Everybody knows about additive manufacturing, but it is not affordable to everybody. So, the reason for me to bring it up is that many of these techniques were originally developed by Scott Crump and others at Stratasys. And I believe that some of it also had, I think Stratasys had bought out some of the patents that were originally developed by IBM. And that is one of the reasons why they had a lot of market. So what Stratasys has been doing is that they have been buying over many different companies. For example, there is a company called uh, Solid Concepts in California and Tucson, Arizona, and some other places. And they have been taken over by Stratasys. So Stratasys as well as 3D Systems have been buying over many competitors, and they have been trying to prevent the competition from taking root. So that's the current status of additive manufacturing, especially for polymers and composites. Of course, there are a lot of new companies like Mark Forged and things like that. Um, so, continuing further, what is the schematic of this process? So, essentially, you are taking a filament of this material and extruding it between a heated nozzle. And this is on a XY table, and after one layer is laid down, this table goes down by a short distance, and then this nozzle comes back and lays down the material again. So in effect, you can say that this is a toothpaste machine. So you are squeezing this toothpaste out of this nozzle and laying it down layer by layer. There are several variations of this. In fact, there is a technique called extrusion freeform fabrication that was developed by the my earlier employer called Advanced Ceramics Research. That's very similar to diffuse deposition process, but that was mainly for ceramics and filled polymers. So there are several limitations to fuse deposition. The process was mostly limited to waxes, thermoplastic resins, and metals with thermoplastic binders. So you had um, acrylonitrile butadiene styrene or ABS plastic, which is one of the most common engineering thermoplastic polymers, polycarbonate, altum, and so altum is a higher temperature material, polyethylamide or PER resins. The issue was that the maximum extruder nozzle temperature is only about 260 degrees centigrade. So the support material is also temperature limited, and the wall thickness has to be over a certain limit so that it can be easily removed. Because if you have a support material, if the wall thickness is too small or too uh, little, when you are removing the support material, it will break the wall thickness. So sometimes you have to remove it using a toothpick or a dental tool, and it is extremely difficult. The extrusion freeform fabrication that we had a higher extruder temperature, like we could go up to 350 degrees centigrade. So we could extrude materials like PEEK, polyaryl ether ketone, or filled PEEK with glass fibers or carbon fibers, which need much higher temperatures for extrusion from a nozzle. So those are some of the limitations of the fuse deposition process. But still, this process is one of the uh, most common ones, because the uh, the process is pretty cheap compared to metal based additive manufacturing processes, and so a lot of people can afford it. Of course, 2600 degrees 2600 dollars is probably not as affordable to a common person, but still it is much better than $100,000. Now, these processes have been well established for polymers and polymer blends, and uh, the same type of progress has not been achieved for high strength polymers and fiber reinforced thermoplastic parts, both short fiber and long fiber reinforced. And the reasons are that you may not find this in many textbooks. And the main reason is that the extrusion of a material. So, for example, here the ability to extrude this material is based on what is called the column strength. So, when it comes down here, it gets liquefied, but here it is still solid. And the strength of this is going to determine whether or not that layer is going to be solidified almost instantaneously. Because if it is too liquidy, then that material will kind of flow down and not give you the um, the uh, accuracy of the part that you are laying down. Okay, unlike metals, it's going to spread out and drool almost. So you don't want that to happen. So this is called the column strength at the extrusion temperature. So, but if it is too solid, then you will need a lot of force to exert at the nozzle tip. So the column force is typically between 0.35 to zero point 0.4 megapascals. I mean, almost like, if you just squeeze it out of a toothpaste nozzle, that's the kind of force you require. So it limits the choice of engineering polymers that can be extruded. And the other reason is that, similar to the metal-based additive manufacturing processes, the addition of fibers and their preferential alignment during deposition, it introduces some kind of an anisotropy in the properties of the part. So you have a limitation in the types of fibers and matching polymers that you can get. So people have been trying to do with carbon nanotubes and things like that, but it has not always worked very well. So the other thing is that when you have fibers, they are anisotropic. So you have thermal expansion coefficient, mechanical properties, etc. That are different in different directions, like in the linear direction and the thickness direction, whereas polymers are typically supposed to be isotropic. So when you combine the two, you are going to have some issues. So when you extrude this material, the fibers and the polymers will expand and contract at different rates. So when it cools down after the component is made, you can have cracks. So if you have a ceramic composite, you need to go through what is called a binder debinding process. So you need to remove the binder, and then it needs to come down to a certain temperature and needs to be heated to the sintering temperature. So when it is taken to the sintering temperature and when it is cooled down, the fibers and the matrix will expand and contract at different rates. So when it is completely cooled down, it would create what are called expansion cracks. So you are not going to get a fully functional part after the part is sintered. So that is one of the biggest problems with the additive manufacturing of ceramic composites. And then the other thing is that um, you're always going to have some issues with support structures. They do not always match with the polymer binder, and so if you have overhangs and undercuts, that's not going to be able to be removed that easily. Now you may have a water soluble support material, but the water may not always, or the humidity may not always um, agree with the polymer, and it may deteriorate the polymer, especially if it has to be heated and dried and things like that. So the two issues with fuse deposition of advanced materials like composites and high strength engineering polymers is that, first of all, the column strength, and secondly, the different ingredients in the polymers and the fibers expand and contract at different rates. So that can affect the final properties and the final component shape. So, but we did overcome a lot of problems. So we came up with what is called a high pressure extrusion head that could be attached to the Stratasys type of a machine, because when you add fibers and when you take high pressure high strength polymers, you need much higher pressure to extrude out the material. So we put a high pressure extrusion head on that machine, and so this is a standard Stratasys machine, and we retrofitted that with a high pressure extrusion head. And it gave us the strength that is required to extrude out that material. So what kind of what types of polymers and materials could we use on that high pressure extrusion head? So we looked at a number of different types of polyaryl ether ketones, PEEK, which is one of the highest strength thermoplastic engineering polymers. And we also looked at reinforcing them with different kinds of fibers. And Lexan is polycarbonate. So we also looked at reinforcing them with glass fibers. And we were, uh, at least we proved the concept that you could extrude out these materials from the high pressure head and deposit that um, on a substrate. Now, could you do additive manufacturing of high strength thermosets and chopped fiber composites? Yes, it can be done, but the there are two possibilities to be taken care of. Um, you need to incorporate the shrinkage into your component design, and or you could have them minimized internally by having um, a gel containing dissolved salts that will cross diffuse and precipitate. So that precipitation will expand and take care of the shrinkage. I mean, the shrinkages are of the order of 3 to 5%. Not a whole lot, but sufficient enough to affect your final properties, final mechanical properties. So that needs to be accounted for in your component and in your material selection. So this was done at the University of Arizona, Sandia National Labs, and the University of Illinois. So they did a lot of polyacrylamide, polyacrylic acids, and they also added fume silica to that to make the mixture thixotropic and control its flow properties. So this was based on some of the earliest um, work done at those places, and some of that work was licensed to um, advanced ceramics research, and based on which we developed the high pressure extrusion head. So the major finding there was that you could have multi-layer stacks of cross-linked hydrogels, and it would so if you blend them together, those hydrogels would individually behave differently than if you were to combine them. So by doing that, you could get a high chain stiffness material um, in order to get the final shape and form. Now, if you had chopped fibers, what would happen? When you extrude these materials through a nozzle, these fibers will tend to get aligned in the direction of the extrusion, and that will preferentially strengthen this material along the direction of the fiber. Now if you recall, this is the same type of behavior that you find in additive manufacturing of metals and alloys. So when you do that, you have preferential alignment of materials in the direction of the extrusion or in the direction of the deposition, which gives you better properties in that direction rather than in the opposite direction. But here the advantage is that you could do, you could do it this way, and then you could do it at 90 degrees or 45 degrees and so on. So by combining that, you could try to get a quasi isotropic material. Now, there is a slight variation of this in which you could combine these materials in different ratios. So you have one phase at a lower additive content, and the other one would be the higher additive content. So for example, if you have the polymer at 80% and fibers at 20%, or if you have a minor phase of a polymer blend, so you have blending polyethylene glycol with something else, with polystyrene with something else. It's called PEOX, polyethyl oxazolene with polystyrene. They both don't blend with each other, but you have a compatibilizer that is added like polyethylene glycol. So by doing that, the polyethylene glycol will mitigate the interfacial reaction between those two and ensure that the polystyrene particles are formed in a fibrous form, okay, and it will create a fiber type of a material. For example, I think uh, let me show you that. I'm sorry, I'm going ahead, but I wanted to show you something here. Yeah. So this is the in situ reinforcement process. So it is polyethyl oxazoline with a talc filler, and you have a high glass resistant temperature styrenic copolymer. So by doing that, what happens is that if you just blended it together, this is what you will find. But during the extrusion process, those styrenic polymers will tend to agglomerate into a fibrous form, and it will form these kinds of fibers. So it creates the process called um, in situ fiber reinforcement. By doing that, it will strengthen this material at the extrusion temperature. I mean, see these particles. I mean, there is no size or shape or form to these particles. But when you extrude them, they tend to become a very nice circular form and fiber. And these are of the order of about 7 to 10 microns. So it is very similar to extrusion or fiber reinforcement with a carbon type of a fiber. So this can strengthen this material quite extensively. So what I want to propose to you is that by doing this in situ reinforcement of these materials, and by combining that with additive manufacturing, you can create engineering polymers that are pretty strong. You cannot find that, or you cannot have that happen in any other kind of a process. So that is the big advantage with the additive manufacturing process in the case of high strength polymers. Now let's go back to where we were earlier. So by doing that, the the fibers will tend to get aligned in the direction of the extrusion. And what is the effect of extrusion on the strength of this material? You can see that it, for example, in the case of high strength thermoset type of materials, it's 8.828, and you reinforce them with MY 720 220 micron fibers. I mean, these are pretty large size fibers, but still, just to show that, with no fibers at all, you have approximately 3 gigapascals modulus. But by adding about 30%, you can increase that to about 8.5 to 9 gigapascals. So you can see that it can strengthen it by approximately, or stiffen it by approximately 3 times. And this is also a function of the aspect ratio. So for example, the longer the fibers, the higher will be the stiffening process. So if you only have an aspect ratio of about 10, it doesn't increase it by a whole lot. I think this should be 4.5 and things like that. This shouldn't be that high. This is 3.00. I'm sorry about that. So you can increase the stiffness of these materials by quite drastically. And You can only get that done by the 3D printing or the additive manufacturing process. Now, you can't increase it beyond a certain limit. I mean, like, 20-30% is probably the maximum fiber reinforcement that you can have. But because beyond that, it's going to clog up the nozzle and it will not allow the material to extrude out, or the pressure required to extrude out will become too high. Now, there are very similar processes that are being used for the 3D printing of actual functional components. For example, if you go to a SAMPI meeting, you can find that these processes have been used to make components for an automobile. Um, I would like you to go in and look at what um, is a process that has been adopted at Oak Ridge National Lab and by a company in Chicago for making components for um, a, a cobra. I mean, not a snake, but a car. Um, and they have used the whole body to be made from additive manufacturing on the shop floor. Like, they would make one whole car within a day or so, attach the um, engine or insert the engine and drive off with that car from the shop floor. So just imagine, I mean, like, this is the direction in which additive manufacturing is going, and a lot of it has to do with the process of uh, preferential fiber reinforcement after additive manufacturing. So here is an example of preferential fiber reinforcement. Um, so here, yeah, this is about 50 microns. So these fiber diameters are about 20 to 30 microns. So what are the effects of the extrusion? You can do that with both thermoplastic as well as thermoset composites. So one of the first people who did that was Paul Calvert at University of Arizona. He and I used to work together on many different processes, and the picture of that was shown on the previous slide. Okay, so these are the mechanical properties in different directions. So you can see that if you reinforce them, so if you have no reinforcement, see the tensile strength 59 megapascals. But if you reinforce them with 38% fiber, carbon fibers, see the strength. It's 257. So it is 5 times the strength of this material. And with very similar elongation, so very similar strain. And see the modulus improvement from almost 2 to 9.4. With polycarbonate also, the improvement is not that high, but still there is significant improvement. So, but what you can also see is that in the parallel and perpendicular orientations, the properties are slightly different. And that is also because of the way the materials are laid down. So, what are the effects of fiber orientation? So, suppose you change the um, angle and test it in a different angle. So, if you have it written in the 0 degrees, you will find the strength or the modulus to be the highest. But if you test it at a different angle at 90 degrees to that, the modulus goes down by half, 50%. I mean, this is only for one particular type, but you can see that it is uh, quite extensive reduction in properties. So let me stop here and upload this as part 1 of lecture 9, and I will continue it afterwards.